Well, good morning, good afternoon, good evening. Everybody, welcome to our third series of oil and gas related webinars from Endress Hauser. Today we'll discuss the important topic of mass balance in refineries. The panel speakers of today, Dr. Osmel Reyes, he is the product manager for calibration as part of our metrology group in our production facility and R&D facility in Reyes in Switzerland. And he has worked on mass balance in several refineries in America, so he has a wealth of knowledge. Our other panel, you see him in the middle as well, is Jenish Gheewala. He is a member of the Strategic Development Group for Oil and Gas in Endress Hauser, and also located in Reyes, Switzerland, same as Osmel. This webinar will last roughly about 45 minutes, 30 minutes presentation, 50 minutes question and answer. But as very common in the oil and gas industry, before we start anything, we'll have a small safety moment. And of course, we will focus on the COVID-19 situation around the globe right now. So please wash your hands on a regular basis. Keep some distance, 6 feet or 1.8 meters from each other. Wear a mask in public. Get vaccinated when you have the opportunity. And make sure that you stay in good mental health as well. My name is Rob Vermeulen, and I'm globally responsible for the oil and gas development of within the Endress Hauser industry, and I reside on the campus in Greenwood. Now, before we start, a small introduction of Endress Hauser. Endress Hauser is a company which is
we have
seems to be an audio issue.
Rob, we have lost you for a moment.
Or you can send a message.
Okay, maybe let me try to cover.
back?
Yes, you're back, Rob. Thanks.
Oh, that's a good thing. So when did I get lost?
When you started introducing
Excuse me?
When you started introducing Endress Hauser Group.
Okay, there you go. Well, you see a nice picture of the introduction in front of you as well. So we're roughly about 14,000 people worldwide, and these are our own people. We're very innovative. We have over 8,300 patents globally for instrumentation alone, which we own. And we are financially very, very healthy with a turnover of 2.6 billion euros and an equity ratio of 76%. So with that, I'd like to hand over to Jenish. Jenish, mass balance, big topic.
Excellent. Yes, a very interesting topic, and in fact, it brings me to the first physics principle. And the physics principle says mass cannot be created, neither be destroyed. Okay, but I would like to ask Osmel the question, which is I think which is common, which is in the head of everybody. What is the main purpose of this mass balance? Is it for financial accounting purpose so that your CFO is happy? Is it for taxation purpose? Is it to ensure that you are still meeting the environmental regulations and you're not flaring too much? Or is it to identify some theft which is going on in your plant? But a bigger, when you're looking at it from micro level as well, sometimes understanding mass balance also helps you understand the efficiency of a particular unit operation. So what, in your opinion, is the main reason for doing mass balance? Osmel, over to you.
Thank you, Jenish. And well, first, thanks to all of you. Welcome to this seminar. It's a pleasure to be with you and with you guys also. Yeah, your question is very interesting because you have mentioned several topics that at the end, all of them are interconnected And mass balance, the result of the mass balance, is also a procedure that gives response or is also related with each one of these topics that you mentioned. Of course, probably the first reason or first connections that we do with the mass balance is that relation between what enters into the refinery, the quantity of products that we are going to use in order to process or to help the process to occur according to the expected conditions, as well as the products that we are producing or generating. It's not, I don't want to enter in any philosophical contradiction with the word generation, but the products that we are creating, again, no contradiction with philosophy, but at the end, what we obtain. Also, we have to take into account that mass balance is not only oriented to measure crude oil and byproducts or finished products. We also have to take into account that mass balance consider other materials, other elements that are needed to conduct our process as expected. So everything, every mass, every material that is involved in our process, in our refining process, is part of this analysis. So again, responding your question, mass balance is connected with all the elements that you previously mentioned. And at the end, we want to know where exactly our product is, our mass, the mass that is entering, or the material, also material balances is another way to call this process. Where is it, what it is, in order to control if they are exactly where it is supposed to be. And if we have some deviation for any reason, and how this deviation will impact other processes, like, for example, you mentioned taxation, okay? But also if our unit is running properly, or if the amount of product that we are expecting to obtain according to some specific process situation is giving us what we are really expecting. So it's connected with everything.
Excellent. And Osmel, you have always preached us in Endress Hauser on this equation. Input is output plus losses and all the other equations. Can you go into more details as to what you mean by generation, consumption, and all the other terms which we see on the screen?
Yeah, this is a very, a very simplified way to see balance of material or mass. Probably one of our attendants can say, okay, this is a little, this is quite simple. Probably it's not exactly like this, and of course it is not like this. But probably we can illustrate in a very simplified way what we are trying to do, what we need to do with the mass balance. We need to do this comparison between the amount of product that is getting in and the amount of product that is going out. But as in every process, in every real process, not an ideal process, we have losses. If we break down this relation between input, output, and losses a little more, then we will have amount of product that is intended to produce or to generate energy for the same process. In some cases, we can even sell part of this energy that is generating the refinery, the outputs that we already mentioned, another part of the product that is consumed by the process itself, probably heating or probably doing some preparation of the fluid, creating some conditions in order to the process occur as expected, plus losses. Losses will be in each one of the steps of the whole process that we are taking. But losses could be reals, could be apparent, but also can be, let us say, controlled. Later on, probably we'll find a more specific word to describe this if we improve our measurement system. Because in all these places, in all these steps, input, measurement, generation, measurement, output, measurement, consumption, measurement, we will have the contribution, bad or good, that our measurement system will give us. At the end, we as provider of measurement system will contribute to improve this mass balance process or to improve the implementation of this mass balance process if we are able not to increase the error or the uncertainty. Later on, we are going to differentiate these two concepts of the measurement system that are involved in the measurement of all these quantities. So at the end, we have inputs, generation, outputs, consumption. Probably we can break down this equation a little more. Accumulation, which are totally connected with static measurement, plus minus losses. And later on, we're going to see or to explain why we say plus minus. But in all of these cases, we have measurement system involved.
So it's a very interesting thing you mentioned, real or apparent losses. Now, when we look at a refinery, let's talk of two examples here. Maybe a small scale or in your language, let's look at micro refinery and mid-scale refinery. But before that, I would like to point out that you always mention this quote, and I would like to just highlight on this. So no matter if losses are real or apparent, in any case, if the product is not properly measured, the refinery will not earn the expected benefits. Can you expand on this quote? Because I think this is something like a first sentence of Bible for anybody who is working with refineries, right?
Yeah, and I think it is a very consistent way to relate our concerning related losses and what we can do in order to reduce that losses. No matter, again, if these are real losses or actual losses or apparent losses. And probably one consistent way to do that differentiation or to reduce those apparent losses and only concentrate in what is actually losses is improving our measurement system. And that improvement have a lot to do, is quite related probably with this topic that you mentioned before. Probably we can do this illustration of what is the impact of different band of error in one measurement system in a refinery.
Excellent. So let's look at two examples, one micro refinery and one mid-sized refinery. Why don't you explain us in detail how much real and apparent losses we could expect?
Yeah, this is a very interesting topic. And of course, it's a general approach to that topic, which is very, very complex. We are not trying to simplify it. We are just trying to illustrate what we want to say. When we, in a project or in our daily life, improving step by step, small measurement installation, not necessarily we have to do a big project, but probably we can do this gradually. And in every case, when we start to reduce our band of error, uncertainty, but using, in this case, uncertainty not as a metrological concept, but the capability that we have, or the absence of capability to differentiate what exists and what doesn't exist. And this is an uncertainty. But if we are able, improving our measurement system to reduce that band of uncertainty, then our losses, whatever it is, will be inside. We will be more capable to differentiate or to detect any loss. And at the end, these losses have a great impact in the performance, economical performance of the refinery, just to mention the economical performance. In numbers, if we are working with the band of error of 5%, and we are able, in practical terms, to reduce that band to 1%, which is a practical and achievable target, then we are reducing a band of money, in this case money, from 20,000 to 4,000, with a difference of 16,000 per day. It doesn't mean that we are going to put this money in our pocket. Unfortunately, it's not like that. But what you can be sure is now we can differentiate, we can identify just what we will be buying only in a band of 4,000 US dollars, not in that big band of 20,000 US dollars. And this is in a very small refinery, 20,000 barrels per day. You know that this is a very small installation. Imagine in 150,000 barrel per day refinery. It's not a big refinery, but it's bigger than the first one. And we can see the impact of this same investment. Let us assume that we are doing an investment in that case in order to reduce our error band. And now we are having a reduction of 100,000 US dollars per day. Again, not in our pocket, but we know where it is. And we know that not more than 30,000 US dollars per day will be the quantity that we are not able to see. This is the idea.
Thanks, Osmel, to clarify this. Now, the thing is, you have covered the situation of achieving a plant-wide refinery mass balance. Now, let's look at the situation of unit operation mass balance. And I know you are a man of you're a man of equations. You basically like to go into details. So we have the slide, and please explain us what does it mean for having a unit operation mass balance for a distillation unit.
Okay, again, this is a general approach. Of course, we are not considering here details, but in general terms, we are considering or comparing, trying to make a balance between the flow rate, volume of product that is entering in our atmospheric distillation unit and the cycles that we are obtaining in the different levels of this distillation units. But this comparison, in principle, will be done in volumetric base, because this is the tools, the instrument, the capability that we have most of the time to measure, or it is played, and you know, these kind of instruments. At the end, even measuring in volumetric base, we need to convert that measurement in terms of mass, because what we are interested to know is the mass balance. And for that, we need to use some conversion factors basically connected to the specific gravity of the fluid. And this specific gravity is not always what we are expecting. That introduce error, that introduce, and it's totally the opposite of what we want to do, that is to reduce this band of error. That's why at the end, this approach of doing volumetric measurement and converting this volumetric measurement to mass in order to obtain a mass balance is a kind of limitation that we can overcome using other approaches.
Great, excellent. So, as in when you mentioned ADU, I'm sure we can extend this principle of having mass balance not only to distillation unit or fractionator, but we can even take this approach to understanding how the mass balance is done. This is your famous diagram. I think you would like to also mention something about here.
Yeah, probably this is an explanation, or probably a way to illustrate what we have mentioned before. In this case, we are maintaining the same measurement points that are regular in a distillation units, measuring the feedstock as well as the yields in the different cycles, as well as the recirculation loops and all the things from the top to the bottom. But in every case, in every place where we are interested to improve the measurement, not in all the cases, because we have, for example, pump around measurement where it's not intended or necessary to have an improvement or a change of paradigm in the measurement. But in those places where we have represented a mass flow meter, in this case, a Coriolis flow meter, is where we are reducing, simplifying, and improving that conversion, that process that we mentioned before. This conversion is eliminated because we are having a direct mass approach.
Yeah.
And
so,
this same diagram, this same idea will be also implemented in other units, and probably we can have an illustration in terms, in terms of equations, okay? the same idea, what is entering as a feedstock in our unit and what we are obtaining as a result of the more complex process that take place, for example, here in a hydrocarb cracking, in the this is hydrotreating units, BGO, and another hydrotreater processing other feedstock. The process is more complex, but at the end we have defined places or positions where the product is entering into the units and defined position most of the time associated to a distillation column where we are going to obtain the different products. These are the places where basically we can implement this approach. Again, just to mention, the mass balance is not limited to those points, but probably these are the more important, more relevant when we talk about the main measurements.
And also when we talk of achieving unit operation mass balance, Osmel explained the example of hydrotreater, but you could also look at fluidized catalytic cracking or any other operation which you have. There it helps you actually understand what is the activity level of your catalyst. It helps you optimize, make it more efficient, your process, and you can achieve this by having a proper mass balance itself. Now, Osmel, you have explained all the reasons why one has to go for a mass balance, not only at a plant-wide level, but also at a unit operation level. So now let's look at, one second, some of the examples which you shared with us based on your experience when you were visiting a lot of refineries. And I cannot explain this in detail because this slide is in Spanish.
Yeah, this is simple summarize of the mass balance procedure. At the end, we have also connected with this mass balance an estimation of the total losses that we are going to have. And these total losses are again connected between the difference, what is going on, entering, and what we are obtaining, of course, taking into account known purposes or known destinations of products that we consider not as losses. And this calculation of losses, 3%, you can imagine how much this 3% represents in a refinery, is something that is what we or what the persons in charge of this procedure is assuming as losses. If we have a very consistent, a more consistent measurement system, we can rely more or less in that value. And this more or less is nothing but money. That's why we need to be the most consistent as possible in order to say, yes, these are my total losses. And these losses are produced by physical issues, by technological issues, or topics that we cannot approach, we cannot solve, and we have to deal with that. But it's not because I'm not able to see, because my measurement system does not allow me to see. And this is the idea. Reduce that uncertainty, improving our measurement system.
Yeah. And also, I'm sure.
Question, Osmel, what is the best you've ever seen, and what is the worst you've ever seen in practical situations?
Well, this question is very interesting, because this best and worst depends on several contexts. Of course, is evolving in time, but nowadays, what we could consider an optimal approach is to use the proper principle of operation, combining static measurement with dynamic measurement, and trying to, wherever is possible, having a direct mass measurement. Whatever is possible to control directly what we want to know, which is mass. From my point of view, every time that you substitute a static measurement, whenever it's possible, for a dynamic measurement. And this dynamic principle of operation is based in a mass approach. You are obtaining an additional result. And in this case, I have to talk about our experience as Endress Hauser. We are going beyond the simple mass approach. We are capable to measure, to detect, to identify, and also to correct the effect of other magnitudes or properties of the fluid. So the result, the final result of our mass approach is not simple because we are measuring mass. It's because we are able to convert or to correct or to improve the result, taking into account all the influence that we can have.
Okay.
Excellent. You already touched on this topic of static and dynamic balance. You also talked about in your famous equation, input is equal to output plus losses plus accumulation. That's the point where I feel there is a bit of shift which we are expecting, because in oil and gas industry, we always hear of the term barrels of crude oil and barrels of output products, which are produced liters of refined products. Now, when we are talking of mass balance, there is this unit which becomes very important, density. And I'm sure you have seen a lot of density measurements. So what is your proposal? How do we move this whole industry, which has been talking in terms of barrels, in terms of volume, to go into mass measurement, but without losing accuracy?
Okay, let me first say that refiners, and I consider myself 50 or 60% refiner, we are conservative because of the responsibility, economical, strategic, social responsibility of the person that works in a refinery. That's why we are very conservative. That's why we are all the time sticking to the standards, to the approved procedures. It means that when in a refinery, you are going to measure density. The first approach and the most probably reliable approach is lab measurement, in order to follow a known standard, international standard that everybody trusts and rely in. But technology move, and most of the time it's better and give us benefits. And this is probably the things that we should do as a provider of measurement solution, to convince or to let our customer know that there are some other approach that are also trustable and can be gradually being introduced and demonstrating that they are very reliable and they have and bring benefits. I mentioned that because, for example, when we implement and start to rely in a density measurement, in an inline density measurement, we are saving time, we are doing the things right, we are also following standards, other standards, and we are giving and having benefits and reducing also, and this is a fact, reducing also uncertainty. That's why for us, for Endress Hauser, improving our capabilities in density measurement is so important, because this variable density is the bridge between volume approach and mass approach. We can do that alone with some approach that later on we are going to discuss, or at least to show, but we can, and we in fact integrate that capability in our measurement, flow measurement devices. That's why we try to integrate that feature every time we can, in order to improve and give another alternative also reliable.
Excellent. Now that you mentioned the point that instead of maybe taking every single sample to the lab and bringing it back, this is to make sure that the physical sample itself doesn't change in terms of property. But when we look at a refinery, when we look at this particular measurement point over here itself, this is the one which has a physical fluid flowing through it. The physical characteristics, physical parameters like viscosity, density, they change maybe even in a day, maybe during the seasons. And how do we actually not have an influence on the measurement even in those situations? Can you cover the topic of how to improve the accuracy even in changing inlet condition? Maybe we are getting crude which is very viscous, so how do we make sure that we still get higher accuracy in those situations? Osman.
Yeah, yeah. In this case, Jenish, we have different approaches, different ways where we are addressing that interesting topic. Probably our capability to deal with fluids that have some presence of a second phase, or fluids that have a change in density, and we are directly measuring that density. But probably one of the most interesting contribution that we can provide to our customers is how to improve even in conditions of low Reynolds. And later on, we are just to mention what does it mean. But basically, we're talking about a product that is highly viscous, how we can also deal with that conditions that unfortunately was not initially, when this technology was started, identified properly, of course, because the experience and the daily work have give us feedback and also opportunities to improve our response. And this topic regarding viscosity is probably one of the most interesting contribution that we have done lately. And it is nothing but, or is based on our capability to measure, again, or to estimate consistently properties of the fluid, in this case, viscosity. Probably we can move to the next slide just to show what we are talking about. If we have a very high viscous fluid, it means, if you see this expression in the bottom of the slide, connected with a high viscosity, low Reynolds. This low Reynolds represent or produce a thicker thin layer. This thin layer that should be very thin start to be thicker and start to be a kind of restriction and a kind of counter effect to the oscillation of the oscillating tube of a Coriolis. And this will produce underestimation of the real flow rate that is crossing through the meter. And this is something that affects basically when you have a large pipe, okay, and you are dealing with a viscous fluid. And this is a very common situation in most of the refinery of the world. And the impact of this effect could lead to the meter to have a behavior that is outside the expected band, the expected error band, even the expected maximum permissible error stated in the standards. Again, refiners are conservative. We want to follow the rules. We need instruments that help us to follow the rule. And this is what we are providing. This is what we are proposing. Something that even in non-expected or non-ideal conditions, remember that 50, 100 years ago, what we had were very light products, very light crude oils. Now, standard products that we are processing most of the refinery, or an important part of the refinery all over the world, is heavy product. We don't have that nice product that we had long time ago. So we have to deal with that, and even under this condition, we have to fulfill what the standards state as requirement. And this is what we can do with this approach of Reynolds number correction. Probably, yeah.
So what you mentioned is we take into consideration the effect coming from the viscosity changes, the physical parameters, and how easy is it to integrate these changes during my calculations? Because it's all about calculations, and that's where the meter factor comes into play, right, Osmo?
Mm-hmm. 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 And this is exactly the how to close that loop, because we are able to measure or to estimate viscosity. We are able to calculate the Reynolds number, and with that Reynolds number, we are able to do a correction. With this correction, now we are able to do a calibration of the meter and calculate new meter factors. And now we can see two levels of improvement. The first one is the meter itself with the capability of improve or correct its performance, taking into account the influence of the low Reynolds dynamic conditions. This is, let us say, the first step. But there's another step when you can dynamically use this meter factor and describe the mapping of the performance of the meter in a flow computer with these values and reduce even more the band of error and improve even more the performance of the meter. This is the first example. This is the meter fulfilling the requirements of the standards, even under this complicated low Reynolds condition. It means a very high viscosity, less than 2000 in Reynolds number, which is a very high viscosity. Even under this critical condition, the performance of the meter is totally, definitely, by far better than the standard. But we can go beyond. We can do this correction dynamically, putting this information inside our flow computer, putting this collection of meter factors inside our flow computer, and having this even more stretched band of error that we have seen before. So you can see that it's a gradual improvement and is definitely a relevant contribution to deal with the real process condition of the fluid.
Excellent. So we covered two important topics in the last couple of minutes. One was improving the density measurement, and the second one was to take into consideration changing physical property conditions and correcting for it in real time, so that every time we make a measurement, we have a higher reliability on every measurement we get. Is that correct, Osmel?
Yeah, definitely. Definitely, we are connected with the dynamic or changing properties of the fluid and taking this information in order to improve our result.
Excellent. So I think it gives higher improvement, but again, the question comes back, because refineries have been existing for a long time. What are your, Osmel, what are your new answers? Because I know you have been with refineries for over 25 years now. So it would make sense that you give us new answers to the same questions which maybe you experienced or you faced when you started working with refineries.
Yeah, definitely. Yeah, well, I'm getting old, but I've seen different perceptions, different reactions of the refineries, including me as part of that big army, with the technologies. And when we started to, or we are still rejecting some new technology that were coming, because we did not rely in that technology at that moment. And we have seen the evolution of the technologies and how reliable they have become in time. And now we can trust, definitely, and we can see all the improvement that this technology brings, the benefits that this technology brings. And for example, in these 4 examples that we have there, I'm starting from the bottom, left bottom, this prosonic flow, ultrasonic compound approach. Nobody trusts in that approach. Long time ago, we are just using that as a survey meter, just to have a rough idea of what is going on. But nowadays, with the achievement that we have, 1%, 2%, even, we can compare and even improve the results that we are obtaining, for example, with an orifice plate, without taking care of having modification during the installation. consistent and being reliable even in high temperatures. That was a limitation that we have with this technology before. And substituting some points of measurement. In this case, it's not a mass approach, it's a volumetric approach, but reliable, simple, with less cost. Same with ultrasonic principle for gas, very consistent, very robust, and very attractive to use it when we want to improve our result of measurement in some places where, for example, in the top of the distillation column where we still have the fluid in gas phase. Things like large DN ProMass-Q, which is a very strong, very robust meter, but with a very interesting characteristic, very low pressure drop. And in cases or applications like LPG, where we are interested to measure in a very consistent way that complicated fluid that is the LPG, because we have to control the pressure of the line in order to avoid flashing to phases, things like this. This meter makes a great difference because we have a mass approach, we have a Coriolis principle of operation, but with a very low pressure drop. So we are not so concerned about what is going on if my pressure drop falls below the vapor pressure of the fluid and the flashing appears. Another topic that we're not going to deal with that is our capability of, even under these fluid conditions, let's say not radical two phases, we can still deal consistently with the measurement. But this is another topic. And last but not least, premium density. Another ProMass-Q meter with an improved premium calibration density, plus minus 0.1 kg per cubic meter, is very, very consistent, and is something that will help us, together with the other properties that we have mentioned, to do the real conversion between volume to mass, and also to help our measurements, for example, in a terminal or in an end product station, where we need to compare the in-field results with lab results.
Excellent. There is also something new which you see on top of each instrument. There is this heart symbol with a bit of ECG on top of it, and that's the symbol for heartbeat technology. Because when we are doing mass balance of a unit operation or for a plant wide itself, then you want to be sure that the measurements which you are doing, they are reliable or not. And you can verify your measurement system by just running simple heartbeat verification. And all these instruments which you see, they allow you to do verification remotely and in a documented way, so that when you are doing mass balance, you can be sure that you are getting real losses information and not getting influenced by apparent losses which could come because the device has any kind of buildup or erosion of the tubes and etc. With this, I think we have covered a lot of ground today, Osmo, and we would go back to the summary while Rob will help us with all the questions.
Okay, excellent. We do the summary now, or we are going to?
Yes, we do the summary now so that we can look at the questions in the meantime.
Okay, well, this summary, I think that covers basically the topics that we have mentioned before. But instead of reading these points, I would like to share with our colleagues some experience in general. First, the convincement that we, as measurement solution providers, are open to discuss with you guys the optimal, the best solution for measurement solution for each case, each condition, because at the end, the person, the colleagues who works in the refinery are the one who knows exactly the conditions where we need or you need to implement measurement, what exactly you need to improve, and which are exactly the requests that we need to fulfill. We have now a broader catalog of options, and we are able to discuss with you which are the right solution for the specific conditions. Because again, every refinery is particular, and only the person in charge or responsible for the refinery has all the information required to be provided for us in order to give the right response. This is the main idea. We give response based on your knowledge and your requirements.
Good.
Excellent, Rob. Back
Yeah,
to you.
let's go to some of the questions that we got. One of the questions was from Keith, and why do you guys use $20 a barrel? Is that the cost to the refinery?
that was just a value, because if I increase so much values, the bigger the number will be very big. I just want to show the relation.
No, Osmel, I think so too. I think the mass balance with regards to the we could have used $60 a barrel and it would have been bigger figures, and that's all fine and dandy. But it's also about the process and the idea behind the mass balance and how that's being helped to give you some of the financial impact. And making that figure higher does not help, I think, with the explanation of the process. But that's a good one. Then we have another question from Gordon, and he's asking: is mass calculation offered as a service from Endress Hauser?
Mass measurement is offered as a property of our instruments, and combining density measurement with volume, you can also obtain mass. So we measure mass with our Coriolis meter. We measure density also with our Coriolis meters, and we measure density also with our dedicated Coriolis meter to measure density.
Yep. And then we have another question, and the question is on the level measurement on the columns, Osmel. The question is, do we need to have the level measurements on the columns in mass as well?
Yeah, of course. I mean, these are different proposals for the measurements. We were more concentrated in dynamic measurement related with quantity determination, input and outputs, but there are some other dynamic and static measurement inside the column, more process oriented, that we didn't mention. One of them, and very important, of course, is level measurement, and probably we can organize a seminar to discuss this topic more related with process measurement. And of course, we also have some proposal in that direction, but not covered today. Today, we just put this atmospheric distillation unit. There were some additional measurement, but we were only concentrated in dynamic measurement related with the mass balance. The quantity of product that is stored in the bottom of the column, and it's a kind of accumulation in that process unit, of course, that have to be taken into account when you do a mass balance.
Okay, last question, because we're running a little bit over time as well. And it's a question from Atta. If we use a Coriolis meter for density measurement, could it measure density when the flow is stopped, but the meter tubes are still with fluid? So I think it's how is it determined density when flow is going through? Or do we need to stop the flow in order to determine density? Okay,
this is a very good question. Remember that in our Coriolis meter, we are combining two, let's say, two different approaches. One thing is Coriolis effect, is that famous phase shift associated to the quantity of mass that is flowing through the meter. But density measurement is not connected to that. Density measurement is the natural frequency that the system will reach when you excite the system, and it goes to that natural frequency depending on the solid characteristic. When I said solid, I'm talking about the system, the mechanical system of the measurement installation. But the fluid and the density of the fluid that is inside the tube is part of the system. So that density will change that frequency. And it doesn't matter if the fluid is stopped or is flowing. In any case, we will have a response, a different response, if the density of the fluid change. Of course, for calibration and for specific measurement, basically connected with calibration, we prefer to have steady flow. Okay, but no matter if we are in steady regime or in dynamic regime, the system will respond if with the change of frequency, if the density of the fluid also change.
Yes. So the answer is we can do it both dynamically, statically, but preferred under static conditions, but make sure that the tubes are filled.
Okay.
That's important.
That's correct.
Don't make sure that the gas and fluid in the same pipe, and then you try to measure density. That's not going to work. So, very good question. Before we end the webinar, I'd just like to point out that in the handout we have some stuff you can download that might help you formulate a little bit better the mass balancing in your plant as such as well. Of course, you can always send us the information or ask questions to either Dr. Osmel or Jenish or myself. Our emails are very simple. It's first name, last name at endress.com and a dot in between. So that's no problem either. And with this, Osmel, thank you very much, man. I think you can talk hours and hours about this topic because I know it's very close to your heart. And you love talking about it as well. So thank you very much for sharing that information. Jenish, thank you very much for moderating and also helping to formulate it in very practical statements, because sometimes with all those formulas, it's not so easy to understand the combination and make it very practical. So thank you very much for that as well. So with this, everybody, thank you very much for participating. Next week, we have a new topic, same time, same place. So please sign up. And if you're interested, always something new to learn, I think. Thank you very much and have a great day and talk to you soon. And with this, I will end the webinar. Thank you.
Thank you.
Thank you. Thank you.